over some of the homework. So just sort of briefly discuss some of these things. Chapter 1, Introduction to Becoming a California Naturalist. Anybody 3 goals of the California Naturalist program? Anybody recall off the top of their head?
Observe.
Observe. Observation. That's important.
Become a link between the academic and everyday.
I think that's a really important one, right? And so we're about becoming these ambassadors for the natural world and sort of translating what can sometimes be difficult for the layperson to understand science and making it really digestible. That's a big part of what we're trying to do.
I think mine was similar to provide science-based environmental education.
Yeah, very much so. Jennifer?
I forgot what I was going to say.
Lost it.
That's not it.
Advocacy and awareness.
Raising advocacy and awareness, definitely. That's a big part of it. So, okay.
Oh, I remember.
Yes, Jennifer.
To appreciate the system that the UCs have, for like, you know, the whole area, like the,
All the natural reserves?
yeah, you know, the reserves,
Tell
all the
this
things
girl
we
to
do,
go back.
and, you know, I don't know, I wrote it down. I can't remember.
That's good. That's very good. No need to apologize. All right, so we're going to harp on this a little bit early on, but California's climate, how is that related to these global factors? How is this part of a broader global set of conditions that create climate? Do you recall?
Yeah,
Carrie?
it was our longitude and latitude, which would be along with that.
Yeah, so we have the Mediterranean climate. We're on the western part of a continent with cold water next to the continental crust and with the westerly winds. Exactly.
I think the thing that's most striking to me is the length of the state. So we're not only in that zone, but we're perpendicular to it. And it's that part of it that seems to be the most striking thing to me.
So the political boundary, how it overlaps this geographic province. Yeah, definitely, you know.
Not a narrow, wide state. It's a very long.
Definitely.
With a huge mountain range running down it to make the weather on both sides.
Yeah, definitely. So having the mountains where they are, those orographic effects, having lower mountains closer to the coast, so you don't have a huge rain shadow going out. You know, the clouds go over, and then the Sierra is really that trap for the orographic precipitation. We're going to move on to water. What are some of the important implications of the chemical properties of water? I think that's really important, understanding that why water is such an incredible substance.
Polarity,
Its polarity.
so easily combines and decombines.
Yeah.
Elements.
So those hydrogen bonds, really versatile.
Ice is less than 10%, the solid form is less than 10%.
Yeah, so it's kind of anomalous. Yeah, the 3 phases are pretty readily achievable within our climate. You know, it's not like mercury or something that takes quite a bit of energy to start to evaporate.
This is not related to this, but what's heavy water? I've heard of heavy water. What's that?
And then nuclear bombs are.
Yeah. Is that still water?
No, I don't believe that it's natural. It's not naturally occurring. It's got an extra hydrogen.
H3O, I don't know.
Okay, never mind.
No, it's not. It's, you know protons, neutrons, and
Yes.
electrons. 99.99% of the hydrogens in your body have just 1 proton and 1 electron buzzing around, no neutrons. Okay? They don't need it. Every once in a while, when a star blows up and forms these things, an extra neutron does get stuck in the nucleus. So it's still a hydrogen because it has one proton and 1 electron. It just has an extra neutron in it, so it weighs more. So it's heavy hydrogen. So it's still H2O. If you drank it, you would know. The problem is that it will decay radioactively and give off stuff. Right? And then when they say heavy water, like in nuclear bombs and all that, because it has that extra neutron in its nucleus, if you surround nuclear fuels with it, they can trap some of the decay products as the nuclear fuel rods decay and heat up your water. So heavy water just has an extra neutron in the nucleus. You don't
It's
make
not
this.
naturally.
Oh, no, it naturally occurs.
Okay, I
It's
was,
as a product of other radioactive decays.
okay.
One of them were able to, plus when the universe was started, when all the Big Bang occurred, they made all this hydrogen and helium. Every once in a while, some of them was like, just because it's carbons, there are carbons in your body that have just an extra neutron. Just one in several hundred billion of them. That's all.
Heavy water. And we kind of talked around this, but I think, the idea of surface tension is a really important part of water. The fact that it has those bonds that have that support right there on the surface winds up becoming a really important implication for a number of reasons. So what about aquiclude and aquifer? I realized that there was a typo. It was quaaludes, which was a little embarrassing to realize yesterday. Yeah, so aquiclude rather than quaaludes. Adele.
It's a barrier to groundwater movement.
Definitely, and then the aquifer.
Is storage.
Exactly. Yeah, so we're just talking about where the water goes once it goes underground. I had a friend in Tucson. He was a hydrologist, surface water hydrologist, and he always joked that once the water goes underground, surface water hydrologists go like this and say it doesn't exist anymore, because groundwater hydrology really is an extremely complicated, where does that water go? How does it travel? How does it absorb? What are these parent materials that it's absorbing into? How readily accessible is it? Those are all, and you can't just kind of go down there and have a look and see, so it's really difficult to understand. So these ideas of aquiclude and aquifer wind up having really important implications for our drinking water and that 1% of water on Earth that is fresh water. So that's pretty important stuff. Yes.
Is it true that we have not really done much research about that, right? Like, we're just now thinking that the farmers in the Central Valley have taken more groundwater than we thought, but we don't have good documentation, right?
Yeah, I'm under the impression Allie may have a little more background on this, but I think groundwater hydrology, because of the difficulties of understanding it, is really being revealed to us at a different rate than surface water hydrology, which we've been able to readily observe for since the scientific revolution. Allie, do you have any thoughts about that?
Yeah, there's a great understanding, there's just not a great public understanding, because groundwater in California is not adjudicated. So whoever gets to it first can pull it all out. Unlike surface water, which is adjudicated, unfortunately it's not adjudicated to us, the people, it's adjudicated to a lot of corporations. But the adjudication of surface water has been around since the 1870s. And it all started here in the county, I think I mentioned that. So, but they're working on it now. There's a bill right now. The first adjudication for groundwater in California took place last month with the Sacramento judge adjudicating a Stanislaus County farm. Meaning that the water was declared owned by the landowner. Goes underground.
Okay, so with an aquifer, and the water can travel great distances, so it can traverse different properties. How do you reconcile that? That's interesting.
Well, this is one of the biggest problems with fracking. It's because you have production waters being put down into the ground, and whether it's if it goes into an aquifer, it would be okay. But a lot of times it leaches into the aquifer through limestone or other porous rock, and it gets into the aquifer and it pollutes the potable water.
Monterey Shale. That's relates to our geology lesson today. Tina?
Well, like one of the stories that I cover constantly, I'm a journalist, is the Tejon Cummings County Water District. And all the water up there is adjudicated. And
Almost all of it is.
They know to the acre foot how much they put in the ground, the water bank, and all the different agencies, the different community services districts, the cities. They know what they put into the ground and they know what they bring out of it. And right now they're doing a study of the wells that have been put in since the adjudication in 1964. And all the farmers say in Cummings Valley, they agree to not pull out. I mean, there's a certain, I can't remember what the term is, but there's a certain amount that you can pull out without depleting the groundwater. And they all adhere to that, even the big corporate ones. And I think that there may be another aspect.
It's called overdraft.
Overdraft, exactly. And they adhere to those guidelines.
And when you say they, you mean in what area are you
Well,
talking about?
Cummings Valley, you know, too, Tashi? Cummings Valley is there. It's well, there's a lot of agriculture, and Grimway, there's a lot of carrots. There's a lot of there's a brand new what do you call it with the water, just hydro
Dam?
Water right?
no water bank. Where you grow without putting it in the ground.
Hydroponics?
Yes, huge hydroponics. And they all have to agree. They all, because the adjudicating, the water master is the Tejon Cummings County Water District. And they pretty much control what goes on with the water there. That's Cummings Valley, Bragg Valley, Tejon Valley, just extend all of there.
So they know how much is left in the aquifer?
Yeah,
Do they have wells?
you mean
Is
to
that how
measure it?
they're-
Yeah, how
Is that
do
how
they
they're
measure
getting?
I don't know. Well, there is a certain extent of not knowing how much, they know how much they put in, and there's a lot of water banking they're looking at. I mean, that's the way it is up there.
Definitely. And so, but it's not mandated by the state, and I think that's sort of the point from a statewide perspective is, there are these sort of anomalous cases where you have organizations and political institutions that are able to come together and come to some sort of understanding. But from a statewide perspective, that's the exception rather than the rule. And typically it's, private landowners' rights, and it's time. Whoever gets there first has the right to it, and the state doesn't really say. And another issue with water in the state, and we should move on to our lecture, but is that you only have to prove 20 or 30 years of water availability in terms of development as well. So that's another issue in terms of these water rights, and what happens when you're looking at the generations out. You're saying that's a load on the water system, and so water policy in the West is definitely suspect, and water policy in California is no exception to the rule. Suzanne, did you have a question or comment?
I was just going to say that I didn't understand a lot about the adjudication of oil rights, but wouldn't water kind of meet the same kind of ownership?
I'm not sure about a lot of that.
Didn't water just drill down into the oil? It didn't matter where he was. He accessed it. It didn't matter whose property it was under. He took it just by drilling down on his property. I mean, it's a difficult question, really, the ownership of things under the earth. And do they belong to everybody, or do they belong to whoever takes them?
Yeah, I think, unfortunately, in a lot of ways, it belongs to whoever can pay the most for it.
There are mineral rights that are you can buy a piece of land that doesn't have mineral rights.
Yeah.
And the mineral right owner can develop the minerals under your land.
Well, that also goes for water.
But for
Yes.
viscous things, I mean, where is the boundary really?
And that's why the surface is underground, because it's in a geographically bounded area where you can say that's where the water goes. It's in this convoluted network that is very difficult to see, and it's extremely expensive to map. So it becomes a sort of no man's land in some ways, where really it becomes a political issue rather than one of science or empirical understanding. And I think that's where you start to see a lot of these conflicts happening. So it's clear that everybody read and paid attention, and that you all are getting something from this. And that's all the homework is there for, as far as I'm concerned. It's just about keeping that check and keeping the standards high. So let's move on to some of these landforms, geology, geomorphology, and then we sort of transition also into soil building, the process of making soil. And I'm not a soil scientist by any stretch of the imagination. Soil science is fascinating. It's an amazing field of study. And last year we had an NRCS soil scientist come in. He was extremely knowledgeable, but he was kind of up here, and it was a little bit over everybody's head. So we have some geologists coming in, but I definitely, you know, that's just to say that I don't know if soil gets the treatment it deserves in this, and I really encourage, there's a good book, a pretty good primer, it's called Life in the Soil, and it's all about soil. It has sort of a bent on gardening, but this understanding of what's going on underground. Again, it's sort of like the groundwater hydrologist versus the surface water hydrologist. We talk about all of these ecological things that are happening, you know, sort of above the soil, but what's underground is equally important for making what we see above ground happen. So I just want to make sure that I impress upon you how important soil is. So let's just talk about California. We sort of discussed some of this when we were talking about the climate of California, but there are all these features. A lot of them are mountain ranges. For the most part, the mountain ranges are north-south trending, but then you have these transverse ranges, these east-west trending mountain ranges, starting sort of from the Santa Monica Mountains and coming up here. The Tehachapis are sort of a transition. They're you know, southwest, northeast trending, but the San Miguelos and a lot of those mountain ranges. You also have, of course, the San Francisco Bay, so the book talks a lot about that being the inlet where a lot of this really cool, moist Pacific air can actually be forced to the eastern portions of the state via the westerlies, those winds. And then there are a couple deserts down there. And just when we talk about the Mediterranean climate and the California floristic province, I just want to make sure you know that we're excluding the deserts, you know, east of the Sierra, the Basin and Range. Some of this is excluded. The Mediterranean climate is really associated mostly with the coast and leading up into the Sierra Nevada, so it's not the entire state that's encompassed by the California floristic province. It actually goes a little bit into Baja and a little bit into Oregon as well. So there are these major features, and it's kind of like a bathtub when you think about it. So when we talk about blue oak, that's a species that tends to grow around the bathtub ring of California. So east side of the Intracoast Ranges, west side of the Sierra Nevada, through some of these transverse ranges, and then these northern mountain ranges at the north end of the valley. So we've kind of gone over this. You've got the Sierra axis, that's this gigantic spine. Yes, Suzanne?
I was going to ask you on that last picture, how does the San Andreas line up with that map? Is there a correlation?
You can see it right there.
Yeah, you can see the San Andreas kind of coming through here. And here's the Garlock sort of coming in this way. San Andreas kind of comes through and kind of comes through like that. Actually, no, it goes up here. San Francisco's on the North American plate. So kind of in this, it goes through Carrizo Plain. Let's go through the Salinas Valley. Let's go like this.
Yeah, it goes right off San Francisco.
Right above San
Yeah.
Francisco.
Just east of San Francisco.
Yeah, so we have this image here, which we can pass around. You can kind of see where the plates align. I had this on one of my cards yesterday.
So San Francisco's moving north?
San Francisco, I think, is moving south because it's on the North American plate. Moving south, the Pacific plate's moving north. So I believe we determined that we are on the Pacific plate right now. So we are moving north. And so that factors into our field site today. So the High Desert Hunt Club is right in here in these Liebre Mountains, and we're going to see some Menak formation, so extrusive igneous rock, extrusive, it came out of the volcano, cooled quickly, it's ultramafic, high in, I think, magnesium, so it's very dark, And its sister rocks are pinnacles up here. So that illustrates the movement, right? So the pinnacles is on the Pacific plate. It's moved north about 230 miles. And then the North American plate, the High Desert Hunt Club where we're going, has moved south a little bit. So it's split, like so.
I think it also goes all the way down to Mexico, with some pieces of it there.
Oh, really? That's amazing.
Yeah.
So we have this Sierra Cascade axis. That's that high spine that runs, virtually to Canada. And then you have these Klamath and Siskiyou Mountains up north. They are they're sort of the top end of that bathtub ring, north side of the bathtub ring. It's also a place where there's incredible salamander diversity. There are a lot of different salamanders that live up there. And then, of course, the Sierra Nevada is one of the largest features in the state. And we sort of discussed some of these coastal fangs going on. So we have these south coast ranges. That's where you're really starting to get into those golden rolling hills, Santa Lucia Hills, things like that. Big Sur starts to get pretty arid, and then the Peninsula Range down in San Diego. You got lagunas, Palomar, Chocolate Mountains, things like that, and the transverse. So we're sort of right there in that transverse zone, going from the Santa Monicas and then moving north. San Gabriel's are a really large transverse range, San Bernardino's. And then we have our two deserts. So the Mojave Desert tends to be a higher desert. So again, when we were talking about that topographic relief of the ranch itself, Central Valley, very, very low. You're talking, 0 to 500 feet in elevation. And then the Mojave Desert, you're talking, 2,000 to 4,500 feet, somewhere in that range. And then the Colorado further south is a lower elevation desert. So when you drive Interstate 8 going out, that's going to take you through the Colorado and Borrego. So we have this notion of cismontane and transmontane, so coast side of the mountains and eastern side of the mountains. And then, historically at least, you have this incredible confluence of really great rivers coming out of the Sierra Nevada through the Bay Delta, really an impressive feature that has been denuded over the years. You also have these old volcanic plugs and these islands that are present. They're sort of anomalous. So let's look at some of the geologic history of California. Of course, cross-section of the Earth. There's this semi-liquid core that we have, and then this mantle, and then the crust. So what we stand on actually represents a very small percentage of this planet, and there are these forces as you go further and further down that become more liquid and more, just liquid, viscous, able to move. So you have these dynamics deep in the Earth where you have these movements that are influencing what happens up here. So that's where you get this notion of the plates. So the crust is sort of floating, like cornflakes on top of a cereal bowl, where if you shake your cereal bowl, it's going to do something to those cornflakes, and that's sort of what's happening. And there are many ways these plates can interact. So, of course, they can be diverging from one another, and these sorts of maps are really great because you can start to see these mid-oceanic ridges where this separation is happening. These are points of divergence. These plates are moving apart, especially this East Pacific, or rather the Atlantic rise here. You have just rock sort of coming out of the bottom of the seafloor, and it's opening up and spreading and pulling the continents apart from one another. And here you have a similar thing. You have this rise that actually comes through, and this is what has separated Baja from the mainland of California. And this is sort of the same feature that starts to factor into the San Andreas Fault. So these are global interactions that we are feeling the implications of. You also have places of convergence, and there are two types of convergence. Is anybody subduction? Anybody have a notion of what the subduction is? Yeah, and so what's going to sink in the subduction? If you're on a plate boundary and it's continent and ocean, the ocean sinks, dense, cold. It's going to sink down. And that often is what leads to this volcanism, because as the oceanic cold, dense plate sinks down, you have this heat and pressure that's building up. And that leads to this magma, this liquefaction of the rock, and you have this mountain building, so you get volcanoes. And then continent to continent, you start to just kind of get this pushing up, like you're pushing two pieces of aluminum foil together or something like that. And that's like the Himalayas, rising extremely rapidly. India broke off of Africa, I don't know how many million years ago, and floated up into the Asian subcontinent, or became the Asian subcontinent, and they've been colliding ever since, and you have these giant mountains. So then there are your transform boundaries, where you have lateral movement. And there are a few different kinds of transform boundaries. You have your right lateral and your left lateral motions. So that's the global scale stuff, right? So those are the really big things. Those are the long time scale. Those are geologic time sorts of events that we're thinking of. But there are, these nested events happening at different time scales. So on shorter time scales, on human time scales, something that really shapes the face of the planet is erosion. And erosion comes in many forms. You have aeolian effects, wind effects, eroding moving sand dunes, making them travel 18, 20, 30 feet a year because you have these incredible winds, or breaking down mountains. You have rain, of course, water. Water is the universal solvent. That's one of the incredible properties of water, so it can break down rock. You also have freeze-thaw. That's an incredible shaper of landscapes, where that's another factor of water, is that when it becomes ice, it expands a little bit. It's less dense, it expands. And so you have these little ice crystals forming in high mountain rocks, and they're just, over time, blasting huge crevices in these rocks and moving boulders, and it's amazing. And of course, human activity. Glacial carving is something that happens on a longer time scale. So you have glaciers that had blanketed much of the high California peaks for quite some time during the last ice age, and they carved the valleys of the Sierra Nevada and the peaks of the Sierra Nevada. And so, once again, time scale plays into this. So some of these factors are really long time scales, but some are relatively short, and even mountain building sort of events can happen over short amounts of time. Ted?
I always think it's interesting that when Muir first explored Yosemite Valley, everyone thought it was a big, gigantic event that dropped the valley floor. And he was the first guy to go, no, this was glaciers. And everyone told him he was stupid, an idiot, a ridiculous lunatic. And it turns out he was absolutely right. And it was, talk about the greatest naturalist who lived, the American and Indian tribes who were here. It's a great shot at that.
Definitely. So, yeah. And again, reinforcing that point that it's not the expert, but the layperson, the really solid observer, the naturalist, that can really make huge strides in our scientific understanding. Greg?
What was the MENAT?
That's, unless somebody has that number, that may be something we have to ask our geologists about. Anybody know, DH?
Oh, no.
Tina?
If Mount Shasta is only 12,000 years old, does that mean there was a huge volcanic event 12,000 years ago?
That means that's when the subduction happened. So I believe that was from the Juan de Fuca plate, which is an oceanic plate. So that was about 12,000 years ago. I guess that was the North American plate, started subducting the Juan de Fuca and built up this volcano as a result.
When you say built up the volcano, we're talking about release of magma to create this, right?
Yeah, so you get this buildup, what's known as Yeah, so subducting, this ocean crust is going downwards towards the mantle of the Earth. It's heating up, it's liquefying, it's very dense. So you get this sort of molten pot of magma underneath and heat rises. It starts to go up, make dikes in the rock, and it depends on the type of volcano. Building is complicated, depends on the kind of volcano, but now you have this mountain building as a result of the subduction, so you have this cone that starts to form with this giant magma chamber underneath, and the heat starts to rise out from that geologic feature. Allie.
MENAC is 23.5 million years old, and it has an annual slip rate of 1.3 centimeters per year.
It's still moving.
Oh yeah.
How do you spell it?
NEENACCH.
When does it move?
1.3 centimeters per year.
So about a ½ inch a year.
You can measure it.
So we have, as a result of all of this geologic activity, we have a huge diversity of rock types in the state. And so, of course, we have this rock cycle whereby the minerals that become rock are continually recycled into other rocks. So rocks are the combination of many kinds of minerals put together, right? So they're just like an atom is made up of protons, neutrons, and electrons. A rock is made up of minerals. And so these minerals get recycled and reformed. And what are the 3 things that it takes to make a rock out of raw minerals? Anybody think of there are 3 main things? Heat, pressure, and the third one? Time, exactly. So heat, pressure, and time. So via heat, pressure, and time, all of these minerals are getting recycled into all of these different kinds of rock. So we have the igneous rock. We've talked quite a bit about that. Those are the lava rocks. So you have extrusive igneous. That's the pyroclast. That's the basalt. That's the obsidian. That's the pahoehoe lava in Hawaii, the rope-like lava. That's extrusive igneous. It's come out of some sort of either a volcano or a mid-oceanic ridge or something like that. Intrusive igneous has cooled very, very slowly, underground typically. So these magma chambers have sat there and they've cooled. The volcanoes become inactive. Erosion or uplift has brought these underground chambers essentially uplifted them, and that's where you get your granites and your monzonites. Sedimentary, so that's sediment. So it's formed by the accumulation of debris. That's where your sandstones, your limestones, which are mostly from calcium carbonate, so that's oftentimes biological in origin, and your cobbles. And then metamorphic. So metamorphic can apply to both sedimentary and igneous. That's when you take a rock, you use heat, pressure, and time, and you reform it. You actually rearrange those basic atoms, and you've turned it into something else. But it's very closely related to what it had been. So limestone becomes marble, or you go to your gneiss or something like that from, I guess, a granite. So we have a number of common types of rock in California. So oftentimes it's granite. Here in the Yosemite area, there's a granodiorite. So now you're starting to, you have this hierarchy, just like with biology. So you start with your type of the rock. It's almost like your kingdom or something like that. You have a type, and then you can get down into these families where it depends on the chemical composition. If you have more potassium feldspar or more plagioclase in the rock, it becomes a monzonite versus a granodiorite. So just like we have the Linnaean classification system, there's a very similar classification system for rocks based on the minerals that form them and their arrangement vis-a-vis one another. So then we have a lot of basalt out here, so that's like that oceanic crust. That's that very mafic, very dark, often associated with the mid-oceanic ridges. and volcanoes. And then these volcanic rocks, these extrusive igneous that we associate most often with volcanoes, so our tuffs, so that's sort of the volcanic ash that's been pushed together, or our obsidian, that's the lava. It cools so quickly, all of the atoms and minerals fall right in line, boom, crystallized. Very ordered structure, and that's why you can have such a great knife edge on it, because it's cooled so quickly. And then you have pyroclast and things like that to lesser degrees. We also have shale out here, so that's often, mud has become shale, and that's the Monterey Shale is, when you talk about fracking, that's sort of one of the big boys in terms of where a lot of these petro companies want to start getting some of that oil, and that's Central Valley. That's adjacent to some of the most productive agriculture in the world. So when we start talking about water issues, aquifers versus aquicludes, this is really important stuff. Sandstone, we have that. That's, I don't know if any of you have ever been to Stony Point in Chatsworth, down in the San Fernando Valley, western San Fernando Valley. That's a great example of sandstone. And chert. And the chert is good for human use. You can do some flint knapping with that and things like that. So very big human history. And then metamorphic. Sanjay.
To add, interestingly enough, a chap that does a lot of hiking up in our area found a very big piece of chert on the back side of Mount Pinos.
Interesting.
So, proof that the ocean was all the way up here.
Possibly, or, I mean, is there any way that it could have been somebody's carried up there? And
I doubt it.
It was big, too big to move?
I don't know. He gave it to the museum, I think. So I didn't actually see the piece, but.
Could have been for tool.
That's what I'm wondering, if it's.
Yes, because I think it was near a Shumash site, so it could be carried up. But I've seen stuff that looks like we've had shelves up on, especially on the meadow side of by Mountain Club.
Definitely, yeah. And so, you get these uplift of some of these things, and in the Tehachapis we see it all the time, because these are time-sensitive events and they can stack up, right? Something can happen 10 million years ago, and then something else can happen 5 million years ago, and then something else could have happened 12,000 years ago, and all of a sudden you have all of these layers, even if it's not necessarily sedimentary rock through and through. Hallie?
Oh, I was just going to say that a lot of the tribe nations there would be people who were artisans, and then people who were the laborers who would bring the large chunks of obsidian or chert and to a milling area. Like up on the current plateau, there's a huge milling area where you see large chunks and then flakes all over.
Mm-hmm. Yeah, so work sites, essentially. So we have our serpentine state rock. That's something that forms during these subduction events from the oceanic crust. It's metamorphic. It's really it's high in magnesium, low in calcium. It's also associated with gold. So it's sort of a precursor to gold, sort of. The mechanisms that create serpentine in these subduction zones often lead to gold production. So in the Sierra foothills, you wind up with fair amounts of serpentine deposits that are strategically located next to these mother lodes. So that's makes it even further reinforces our state rock status. We also have slate and schist. There's a lot of schist on the ranch, actually. And if we have some time, I'll try to show you a map that sort of breaks down. I made yesterday just, igneous rocks on the ranch, sedimentary rocks on the ranch, metamorphic rocks on the ranch. It's kind of interesting. The metamorphics are associated with the Garlock Fault, where you have that plate boundary, or maybe it's not a plate boundary, but it's a transform fault, and you have the heat, pressure, and time happening, and it's metamorphosing into the schist. So we had all these great rivers coming off of the Sierra Nevada, going into the Central Valley. So of course they were transporting more than just water. they were transporting sediment, and that sediment over the years accumulated to be 20,000 meters in thickness, just dumping all of this into a valley that is, there are some outlets in the Bay Delta, but further south, down here, Kern River, Lake Buena Vista, Tulare Lake, a lot of these basins, enclosed basins, so you just get this accumulation of sediment. And that's one reason the South San Joaquin has such great agricultural resources, is because you have a variety of rocks from a variety of elevations from these very large mountains moving through, so you get different soil compositions, and you're in more or less an enclosed basin, so it just accumulates. It doesn't go out to the ocean. It just sits here and starts to build up, and so you get these really deep, rich soils that are extremely diverse. So you can grow a really broad array of crops out here. It's not, you're not just growing corn after corn after corn. You can grow corn and peppers and eggplants and everything, tomatoes, because you have all of the soils out here. I think we've beat this dead horse.
San Joaquin Bay for elevating resisting staff. There's mountain building around, but is the floor itself extends down?
I think it may be denuding, if anything. Allie, is it?
No, it's the erosion from the Sierra Coast Range is actually building it up.
So there's still inputs?
That came out yesterday said that it's actually increased 0.16 millimeters because of the reduction of, or the pulling of the 64 trillion water.
Mm-hmm.
But the Owens Valley is dipping because it's a gravel.
Yeah. Okay. I was conflating the two. So just to, we've talked a lot about this Mediterranean climate. Hot, dry summer, cool, wet winter. So the hot time and the wet time become separated. That's pretty unique among this Mediterranean climate. And then, just sort of this interesting thing that, technically our spring occurs in November. Clearly what we associate with spring in terms of having flowers blooming and the annuals really being productive, that is in the traditional springtime of the northern hemisphere. And there are a lot of evergreen species out here. Greetings. So, of course, we have a broad array of microclimates in California, and that is the result of the varied topography to a great deal. So think about, not only do you have this three-dimensional gradient, you also have your slope and aspect starting to change things, right? So the north faces on some of these mountains are going to have far different microclimates than the south faces, and same with the east and west faces. So you really start to get that three-dimensional diversity that creates the microclimates that really starts to encourage the biodiversity. And so people feel pretty good with these orographic effects. Makes sense. We've sort of talked about this already. California precipitation, as you go south, you become drier and drier. And of course, there is talk about renaming the southern San Joaquin Valley the San Joaquin Desert, because you get only an average of about 5 inches of rain a year historically in these areas. And you have, more or less desert-adapted species, right? Blunt-nosed leopard lizard, San Joaquin kip fox, burrowing owl.
What's the average rainfall on Tejon Ranch?
It depends. It's a gradient. Up top, you get, I think like 25 inches of precip on average a year, and down low, southern San Joaquin, you are looking at, 6, 7 inches a year.
Like where we were on our field trip last week.
So that's Antelope Valley. That actually probably gets closer to 8 inches of rain a year, 8 or 9. What do you find in Enac?
We get about 6 to 7, and we can watch it go up to the ranch all the time. They get more than we do. And we get more than Lancaster County.
Yeah, so I think that's an effect of being so far west in that valley. You're actually getting some of that influence here. These transverse ranges aren't as big a barrier. These are, the wind is sort of going along these ridges. So this western Antelope Valley, you can see it's just a little bit wetter out through here. Yeah, so that's an interesting thing, right? So the Mojave Desert side of the ranch actually gets a little more precip than the San Joaquin Valley.
Precipitation wise, anything that gets less than 10 to 20 years is desert.
Mm-hmm.
And the orography of the transverse range, you can see that it doesn't heat up as fast going down the leeward slope,
Mm-hmm.
so it doesn't dry out as quickly. So that's why the upper Antelope Valley gets more precipitation than most of the other deserts.
There you go. So now let's transition to soil. And I'm sorry, I can't give you more. Soil is fascinating. But to a large degree, soil is being driven by your parent material. That makes sense, right? Because what's on the ground, your basic rock that's there for the longest amount of time is breaking down over time. Water is the universal solvent, starting to break down this parent material, and that's the bulk of your nutrients and your soil composition. So we have a variety of soils. Serpentine soil is one of the most unique soil types in California. We get ultra high magnesium. It's really interesting. So you have these plants that are adapted for serpentine soil. They're used to a toxic environment, essentially. You would think, man, these are super plants. They should be able to grow anywhere. But if you take a leather oak and you put it out off of serpentine soil in the chaparral, that's terribly. It's a terrible competitor. These plants are just good at dealing with the worst situation possible. That's all they're evolved to do. They're not evolved to be really great competitors. They're actually evolved in a system with very low competition. I always thought that was fascinating. Suzanne? No, we have, there is serpentinite on the ranch. You can find chunks of it, but we don't really have extensive serpentine soils where we get those plant communities. There are some. It's largely associated with the western Sierra Nevada and eastern intercoastal ranges. So more towards the bathtub ring. One place that I know has quite a bit is Sonola Loni Regional Park in the South Peninsula, South Bay area. Really beautiful place. There's serpentine outcrops and then really great valley oak woodlands and savannas. Beautiful place. So, no, please.
Can we talk about the Hollister fault in serpentine?
No.
In Hollister, on the San Andreas fault, they've not had any earthquakes in recorded time because it's on serpentinite, which is turned to talc. And instead of earthquakes, they have a continuous creep. So any of the sidewalks or fences or any structure, you can see that they're constantly being shifted. So where you see this grand fence moving during an earthquake event, what happened in Hollister is just creeping along. And it's because of the serpentine creating the talc.
And so that's a closer area where you can find serpentine. Hollister's Salinas Valley, right?
Yeah.
So it's not too far from here.
Kind of almost where the little creative began, but it wasn't in Hollister.
Mm-hmm. Yeah.
And during the 1989 San Francisco quake, there was electrification of the soil downtown. People talked about. How is that related to soil quality and things we've talked about?
I couldn't tell you specifically, but I imagine where you're putting a lot of unconsolidated fill dirt for construction and you are taking water out of the aquifer, you're making the soil structure less dense and so more easily liquefied. Maybe some of our geology professors can talk more extensively about those dynamics. Marie? Oh, okay.
You get liquefaction in Mexico City as well because they built on an old lake bed. So you have groundwater. You have those are sediments that haven't really formed as rock, and they did the same thing up in San Francisco Bay when it filled in there. And so you have water involved, and it's actually like jelly almost. Yeah. There's one of the reasons like Mexico City's earthquakes are so profound is because the ground jiggles instead of just moves like a rigid structure. So.
But Northridge had a lot of electrification too. It's right. My friend's house was a mile from us, and it moved about 3 feet.
And where was that?
Northridge.
I know the Northridge Pike, that's the location you're talking about.
Yes, yes. And it was just it was all about real sandy soil. It was, the whole sandy structure, the soil was real sandy down like 8, 9 feet. It just moves.
That's incredible amounts of energy. So again, talking about soil, nitrogen, so these biotic processes can add nutrients to the soil. Nitrogen is it's readily available in the atmosphere, right? It's like 70% of our atmosphere or something like that. It's a lot of nitrogen in the air, but how do you make it accessible? And soil root uptake is one of the best ways for plants to absorb nitrogen. They don't really do it through their leaves. So there are these bacteria that are able to take up nitrogen really readily, and they live on the roots of many plants, including members of the pea family and the buckbrushes, the ceanothus. And so as they die, these bacterium release nitrogen into the soil, so you have these nitrogen-fixing members of the plant community. So after a fire, you get fire followers, and very often some of these most profound fire followers, like deerweed, it used to be Lotus scoparius, I'm sure it's changed. It's a little pea plant. It's a major nitrogen fixer, so it follows